Okay, so we're dealing with the particle in a one-dimensional prison, so it is forced to live between 0 and L, and we've concluded that it's possible to write the solution in terms of these functions of position, which have this normalization factor. Okay, so that the general solution for the wave that describes this object is going to be some combination that looks like psi nx times the time part, which is e to the minus, in terms of particle properties with the energy, En t over h bar. It looks like that. So let's say that the particle is described, let's pick one of these. Let's say n equals 2. So we choose n equals 2, and we decide that the particle is in this state. Psi 2 of x, e to the minus e2 t over h bar, which is 2 over L sine of 2 pi x over L, e to the minus I e2t over h bar. Again, what's e2? Well, from the boundary condition, right, this is k times x, so we had k times L is n pi, and right, E is equal to h bar squared k squared over 2m, so we can turn this into a k squared equals n squared pi squared over L squared, and therefore this is, we get k squared is equal to 2m e over h bar squared. So we have 2me over h bar squared equals n squared pi squared over L squared. This is E of n, so En is equal to n squared pi squared h bar squared over 2m L squared. And so the energy in this case is 4 pi squared h bar squared over 2ml squared, which is 2 pi squared h bar squared over m L squared. So that's the energy of this particle, and this is the time-dependent function, right? There's both the spatial part and the time part, and we want to get a sense of what it means for the particle to be in this state. So this is supposed to represent some particle that's forced to live in here, and this particle has some energy. So classically, it's sort of moving back and forth, and we want to see what the quantum mechanical description of this is. So we know that the probability of finding the particle at some value of x is equal to, we have to integrate psi xt modulus squared in dx from x1 to x2. Right? So this is the probability that the particle will be found between x1 and x2. We know that if x1 is 0 and x2 is L, that will give us 1. Okay, so let's think of the probability density, right? The probability density is psi of x and t modulus squared right? That tells us the probability at each point, which we then have to integrate over a range to find the probability of finding the particle in that range. But what is this quantity? Well, it's psi star of x and t times psi of x and t, which is root 2 over L, right? This is a real function, the sine part, so there's nothing that changes in the psi star. This part changes, so we get in psi star e to the I e2t over h bar. That's psi star. Now I write psi, which is just this, so it's almost the same. The first part is the same. And then I have e to the minus I e2t over h bar. So what is this probability density? Well, it's 2 over L sine squared of 2 pi x over L, because the other part is just equal to 1. So what this is saying is that the probability density, I can consider any range of x positions and conclude that the probability of finding the particle within any given range doesn't change with time. And so in what sense is this particle dynamic, right? P, the probability density, does not depend on time t. So we're trying to get at an understanding of what's called the energy-time uncertainty principle, which is not a great name, but because it's qualitatively different from the position momentum uncertainty principle. But the key here is to notice that, right, so what we're getting at is a principle that says that delta E is energy, times delta T, where T is time, is always greater than or equal to some number. Similar to the delta X, delta P uncertainty principle, but qualitatively, this is a very different kind of statement. So delta T is not an uncertainty in time. It's really something that we should describe as the characteristic time scale for the system to change. So if there's no time dependence here, as there isn't, then there's a characteristic time which is infinite, right? So a system that's not changing with time changes in an infinite amount of time, in some sense, right? So this quantity goes to infinity in this case, and this quantity can be as small as possible. In fact, notice that there is no range in energies. So it's better to talk about the range in energies. The energy in this case is just E2. So delta E, there is no range, that's equal to 0. So this is similar to what we've seen for the other uncertainty principle. When the range of one quantity goes to 0, the other has to go to infinity. Okay, so a particle that has a fixed value of energy doesn't vary, doesn't evolve in time. Okay, so in order to create time evolution, in order to produce a dynamic system, we're going to at least have two different values of energy.